Hi everyone, Joseph Denman. So I'm going to talk a bit today about the R-chain equivalent of Ethereum's gas, is the best way to put it conceptually, to tie it back to something we are all probably already familiar with. I'm going to talk about a more general pattern that R-chain's version of the same system and Ethereum's version kind of fit, and how that more general pattern allows us some modularity and how we quantify cost of programs. And then I'm going to tell you a little bit more about what specifically we decided to do and what's special about R-chain and how we capture costs. Termination semantics. So the general problem that Ethereum set out to solve, and is one that is prevalent in decentralized systems in general, is that everyone's kind of running everybody else's contracts, right? Well, validators in particular. So, you know, outside of one of these frameworks, without one, there's really nothing to prevent an agent from just deploying a program that runs forever and consuming miner or validator resources, right? So essentially just DOSing the validator. This is going to be a problem wherever the language used to program the blockchain is Turing complete. So in general, the solution is pretty straightforward. It's kind of the obvious thing to do, which is charge people to run programs. And the way we do this is kind of divided into two parts. The first part involves constructing a termination proof for a given program. And the second part involves using that termination proof to decide how much it actually costs to run a program. And these things unify quite nicely. So the first portion, a termination proof. Let's assume a set of states, and we're going to leave them undefined for now, but we'll wrap back to that later. Let's assume next a well-founded set. A well-founded set is like a special kind of set, only in so much as that, in that it defines a least element. So pretty much no matter where I am in the set, right, no matter where I start, there's always going to be an element that is the smallest in the set. Okay, so it's kind of like, yeah. So a good example of that, the set of natural numbers, 0 is our bottom, right? If you have the set of tuples of natural numbers, it's going to be tuples of 0 that are our bottoms. If you choose W to be the set of DAGs, then our bottom is going to be the initial vertex, right? And essentially I'm arguing, or not me, but I'm presenting here that all you really need are these three definitions and a couple more invariants that we'll define in order to find a stopping point for termination proof. Thirdly, a set of operations. So operations take one state to another state. We all know that. And the general method that's being presented here, and the more I describe it, the more obvious it'll become as to why Ethereum and R-chain have used this, was initially proposed by Turing. So essentially 13 years after Turing published his work on the halting problem, he came up with like this general method for proving termination, which is that if you have a program, you can map its states to elements of a well-founded set. And since you know that the set will terminate at the lowest element, you can therefore verify that the program will eventually stop. And it is just for domain specificity, given that we're working in blockchain, it is useful to mention that at least the set chosen must be universal across a validator set. So if the first function, the termination argument search, works to map a state to an element of a well-founded set, and we can recognize that essentially as a gas balance, right? That's what we would know it to be. If the termination argument search would essentially say, okay, given a state of a contract, give me back the gas balance that's available to this contract at a certain point. So once we have kind of a balance function, then we introduce a transition invariant. And the invariant says, assuming that P and P prime are elements of the set of possible program states, that if P can transition to P prime, and the balance of P is greater than the minimum element of the set that we choose to represent termination, and that implies that the balance is reducing from P to P prime, then we know that the balance is decreasing everywhere of the program, and that the program will eventually terminate. Because it will eventually, yes, please.
Now it is on. Good. Just a little detail here on the map. Maybe I'm misunderstanding things, but it seems like, consider the example where I pick the set of real numbers as my well-founded set, or positive real numbers.
Yep.
And then I say that I begin with some P and it has like 1, and whatever I can transition from that P, I'm going to half the value that I have, the real number. And so then it would seem like I would come infinitely close to 0 by always having it, but why? How come the validity check still goes through? Like, so I can half it, I can half my number infinitely many times, and still I wouldn't reach 0. Okay.
So are you assuming like if I said that I'm just going to decrease this by, or decrease something by half every time that I, every time essentially that I move, that I transition? Well, if you choose a set of natural numbers, then when you have a natural number...
Oh, real numbers.
Right, so real numbers are not a well-founded set.
Okay.
Right, so if we choose a set of natural numbers, which is a set of positive integers, then if you half a positive integer, you're not going to get a positive, well...
Okay,
yeah.
Cool. Thanks for clarifying.
Cool. Good question. Excellent. And if anybody else has any questions, feel free. Yeah, I want this to be as interactive as possible. Cool. So essentially this is just a more general proof to say that if the validity check is true for all program states, and the program eventually terminates. And we can add one more thing that Turing didn't include, but that Ethereum did, which essentially allows us to charge universally for computation, and that is a cost model. And a cost model is defined as any function that will take an operation from a set of operations and map it to a cost, right? And since we're using W as our well-founded set, right, then it's just going to map an operation to whatever W is. So we can kind of refine our transition invariant by specifying that the balance of P is reduced by the cost of the operation that causes the transition, right? So if our termination argument search is essentially gas balance, transition invariant is making sure that we don't have any out-of-gas errors, then the cost model is the fee schedule specified that specifies the cost of each bytecode for the EVM, right? So just bringing it back to stuff that we all already know. So in general, right, just to recap, termination argument search, it makes sure that we have a stopping point. The validity check makes sure that we're approaching that stopping point. And the cost model allows us to tune the rate at which we approach that stopping point. So that's the first piece. The problem kind of with just leaving it here is that I could still deploy a program that goes for a very long time, right? And a non-infinitary length of time, right? And that still consumes minor resources, and because the human life is less than whatever a billion years, and that's still very much relevant. Ethereum recognized, as they often do in this domain, that they could leverage the power of economics to enforce good behavior among actors trying, among actors trying to have their programs run. And the solution is to disincentivize DOSing validators, right? And so in the traditional style, they said, okay, we're going to make the actor purchase minor resources. So when you deploy a program, you specify a number of fields. The first thing you're going to specify is a max consumption, right? If this is a set of natural numbers, then this is going to be the largest amount of gas that you want to consume, right? If W is a DAG, then it's going to be the largest DAG size that you could create, right? If it's a tuple, or if you choose W to be the tuple of natural numbers, then it's going to be the maximum value for each component of the tuple, okay? So the idea being that the more you pay, the higher up in this set you can get. And the higher up in this set you are, the further you are away from the bottom element, and thus more steps you can take. Thus, the more you pay, the further you go. But since we're essentially starting an economy here, and we don't necessarily want to standardize the cost of a resource across the entire platform, we also offer, just as Ethereum did, the ability to, or for the actor to specify a conversion rate, which is essentially the actor saying, this is how much rev, or this is how much I believe your time is worth. So this amount of W is worth this much rev. So you purchase the maximum amount that you've specified, or pH_lim, which is the maximum amount you've specified, at the conversion rate that you've specified. And if you have specified a high enough rate, then supposedly a validator is more incentivized to run your program because more will likely be left over, and thus there's a greater miner reward. Lower transaction or lower conversion rates will be less attractive to validators, so they will be less likely to accept the transaction. So when we multiply pH_lim by the rev over cardinality of W, we essentially get the amount in rev that's going to be removed from the deployer's account to pay for the computation. And since that purchases you your initial amount of flow, then you can set that as your initial rate, and we can begin execution. So this is probably a good time to open up the floor for questions.
I'm curious about the cardinality of W. What does that mean? I'm thinking I'm familiar with the Ethereum model where I can specify a gas limit and a gas price. Is that relevant to like gas limit, or how's that work?
Yeah, so this is right. So pH_lim is your gas limit, and the rev over cardinality of W is your gas price, right? But since I'm merely making a point that we can generalize not just have natural numbers be our denomination of gas, but that we can choose any set, right? So if it's cardinality of W, then I'm essentially saying this much rev gets me this much of W, right? But essentially it is, total gas and then the rev to gas conversion rate. So something that's different that we should probably recognize before we continue on is that the R-chain termination model is defined at the source level. So when you're programming Rolang, if you become familiar with Rolang, you'll likely become familiar with the cost for certain syntax level language constructs. If you execute xbang q, whatever q is, then you can determine in the source code the cost of that send, right? And by specifying the termination model at the source code level, we gain independence in, or as to how the language is actually evaluated. So independent of whatever evaluator VM interpreter you're using, if you specify the cost model that's, or a cost model relative to the syntax, and include in the semantics of the evaluator the termination argument check and the transition invariant, then it's accepted as a relevant termination model for Rolang. Cool. So there's the question, though, which is actually turns out to be a little bit more difficult than you might first imagine, is how do we enforce these invariants at runtime, and how do you track what these balances are for a Rolang program at runtime, right? So I believe that the best way is to modify the semantics of the original Rolang itself to include the flow balance and validity argument check and the transition invariant. So if we view p par q as just, say, an arbitrary row-length program, right, which has at least two subterms, p and q, and they're running concurrently, let's think of ph, right, as essentially our flow balance, right, what we're calling it now. So in this case, we've chosen flow to be the set of natural numbers, just for a starting point. And the first rule says that if I've given flow to a program that has multiple concurrent subterms, then I can hand a replica of the flow that was given at the top level term to the subterms, right? And the reason that this is important is because if we just maintain a central counter, if we just maintain a central counter and try to run p and q concurrently, then we get consistency issues, right? So we have to be able to maintain this limit for maximum consumption while maintaining the concurrency semantics of the language. For now, we can imagine pH as a global shared concurrent counter. That's not going to be entirely true. We'll see in the future. But for now, we can imagine it like that. Which brings us to the second rule, which essentially says that if p with pH can go to p prime, modifying pH to pH prime, right, which means that it's decrementing pH to pH prime as it transitions, and that when it reaches its secondary state, p prime, if its flow is greater than 0, right, so if this transition is enabled, then it may happen concurrently. So if p can go to p prime, modifying the flow balance, then we'll notice q witnesses the modification to the flow balance. And thirdly, which is essentially a semantic translation of our transition invariant, says that if pH can go to p prime, pH prime, and it tries to yield a pH value that's less than 0, then the process must halt, i.e. go to nil. So let's run through some examples to bring this kind of back down. In this case, we're deploying a program 1 plus 1 par 1 plus 1. It's basic arithmetic. Now, in the current formulation of the row-lang interpreter, we wouldn't evaluate this because we don't evaluate top-level arithmetic expressions. But for pedagogical purposes, this will do. Let's say that we deploy a program, and that aligning other details. It ends up with a pH balance, initially, of 2. Deploying this program puts it in par with the current blockchain state, which is S. Once it's in par, we can begin evaluating. So we'll notice on the third line, or going from second to third, we're distributing pH across the two subterms. On the fourth line, we're evaluating the left side, 1 plus 1, into 2. And assuming that addition costs 1 flow, we're going to reduce our counter, which is recognized by the term that is yet to be evaluated. When we evaluate the second term, of course, the counter is reduced to 0 in total. Pretty straightforward, right? If we try to do the same thing with the same initial flow balance, except we have one more cost, then obviously, because we don't have 3 flow and we only have 2, we're going to run out somewhere. And that happens to be on line 1, 2, 3, 4, 5, where both of the left expressions have been evaluated, and the third is yet to be evaluated. So when it tries to evaluate this addition, then the entire deployment needs to stop, reducing the entire thing, collapsing it down to nil, and ceasing to consume any more flow. To get a better idea of how payment works with respect to sends and receives, we're going to need a small language to describe how things interact with the tuple space. And this is more general for a number, or more useful for a number of reasons. So let's imagine T is the tuple space, and it is essentially a mapping from channels to data, right? We've seen X bang Q, right? Well, if X is a channel, when I evaluate X bang Q, then my data is essentially going to be Q. But since we have a list of data, remember we can have multiple things into the same channel, right? Then we could essentially have lists of sends, which is the bang at Q. We can have lists of persistent sends. We can have one-time reads, which effectively stores the continuation. And we can have persistent reads, which stores the continuation persistently. And what we'll notice is that we have to persist flow balances along with the programs. It becomes more clear a little bit later why we need to do this, but basically because of asynchrony. So this will probably help clear up kind of what this language means. Assume Alice wants to deploy A, which sends persistently on the channel data feed some data. And in parallel, on data feed, waits for that data, and then once it receives the name, evaluates that data, the value of the data that was sent. So she deploys A, allocating an initial flow balance here. And we remember that, oh no, this is actually a good point. Notice that data feed we're assuming is already in the tuple space. We're saying that data feed, right here, currently has no data. So there's been no action across a data feed as of yet. Right? So it's kind of like a fresh, unperturbed channel. Once we've allocated our initial flow, we can distribute it to the subterms, sending and receiving, respectively. In this case, let's assume that the persistent send executes first. Well, that's going to take essentially data, quote it, turn it into a name, and store it, as you can see down here at the bottom, at the name at data feed, right? So this is essentially expressing what everyone else has been talking about these past couple days about how the tuple space works. And notice that the value associated with, or associated initially with the send has been reduced to pH prime, okay? The reason that it was is because we have to pay for the cost of the send, right? So the first thing that happens is it's reduced. Second thing that happens is that the flow associated with the send is stored with the message, right? Cool. Also notice that since these two share essentially the same counter, that the input at the bottom here, or second from the bottom, has also witnessed the decrease in flow that was caused by the send. Assuming now that the read executes, right, what we're going to get is that data, which is here at the bottom right now, is going to be taken out of the tuple space and substituted into the continuation of 4z coming in on at data feed drop z. So what we should see is drop at data on the other side, okay? And we're also noticing that our flow has been decremented 2 more times. So why? The reason we have to do that is 1, to pay for the input, to pay for the read, right? And 2, to pay for, and I can actually draw this, to pay for the persistent send. So we have to remember that according to the language semantics, a persistent send, I hope everyone can see this, is equivalent to an arbitrary amount of individual sends performed in parallel. So essentially every time that I perform a read from this persistent send, we have to treat it as if it's taking the message out and re-executing the send to put it back, right? So if I do, or if I deploy a persistent send, then I have a persistent cost to executing that send whenever it's read. And we'll see soon how we manage that between different deployments. So in general, that would bring our flow balance down to pH triple tick, right? Noticing that, of course, at data is still in the tuple space and that it has witnessed the decrements. At this point, star at data is evaluated, which costs an additional 1, taking us to pH quadruple tick. And from there, essentially, we have data is equivalent to a nil process, because it's a ground term, and thus is completed. So before going on to the next one, are there any questions? Great. So the natural question is to assume, okay, well, first, I'll bet the question is, when I deploy a contract, okay, does that mean that every time I deploy a contract, I'm paying for the invocation of that contract, right? Since you're saying that once you deploy something, it associates flow with you, right? And then it ticks from that flow every time that the thing runs, am I charged essentially for every time the contract's run? And the answer is no. And this makes kind of clear why. On our chain, we scope who pays for the computation by who deploys it, right? So whereas previously, I had the process that we were deploying as a single process A, which included both of the par terms, okay? So let's say that I split this up into two separate terms, P and Q, which are virtually the same, but that I'm going to deploy separately. Well, by deploying them separately, I indicate that I'm going to give them both separate flow balances, which are going to come from separate wallets. So we can say that Alice and Bob, Alice is deploying P, Bob's deploying Q. So the flow for P is going to be taken from Alice's wallet, the flow for Q is going to be taken from Bob's wallet, right? And that way when they execute, the costs are localized to the things that they execute. And we'll see that we have a very natural way of kind of propagating along through the program trace, the portions of computation which originated from the deployer's original computation. So let's see an example of that. Assuming again that at data feed is empty, and this time assuming that Bob's program, the read, executes first, right? Well, that's going to put a continuation, which is question mark z dot star z. That means when I receive a message, call it z, substitute the body in, and then drop it. Same thing that we had before, right? Noticing that Bob's flow has been decremented by 1, the cost of the read. And assuming next that Alice's program executes, which sends on that data feed persistently. As in the last example, what we should see is that ultimately we get star at data with the cost decremented, essentially for the cost of the write and the cost of the read. But what we should see more specifically is that the total costs remain the same. The total cost for executing the program should be constant. The difference should be in how we distribute that cost, right? So remember in our last example, we saw that we ended with a flow quadruple tick, which means that we should see a total of 4 ticks on all flow balances for this separate computation. And that's in fact what we see. Noticing that after star at data is evaluated, we bring Bob's count down to ph double tick, and that in executing the rest of these after the persistent send, that Alice's persistent send has been decremented by 2. 2 plus 2 is 4. It's the same cost. We're just changing how it's distributed. So this is particularly useful in setting up, as you know, you could probably infer by the example, in setting up, in creating a separation between the sender and the receiver of a message, right? Well, oftentimes we'll want to set up services that discriminate or that separate cost from the agent that's producing the data and the agent that's doing processing on that data, right? I do not want a system where every time I produce data to a public data feed, I have to pay for the computation that occurs as a result. Contracts. So it turns out that the only semantic difference between a contract and a persistent for is who pays, right? In the persistent for, we already determined, right, that it's allocated its own flow balance, okay, so that it can proceed independently of the send, right? Difference being between contract and persistent for, that a contract is not allocated its own compute flow. So after I deploy a contract, right, it sits essentially in the tuple space with no additional way to run until it's given some. So how does it get flow? Well, the dual to contract is the call syntax. Call syntax is effectively an indication of the programmer that they are willing to pay for the contract that they invoke. which is essentially call return style like Ethereum did. So what we see is that we have two options. If I use send and persistent for, then I can separate the costs out, right, allowing for more modularity. If I use call syntax and contract syntax, then I thread the flow associated with the call through to the contract. And as my comments indicate, it's useful for discriminating when, or determining when you want to pay. And also worth noting that sends, x bang q, will not synchronize with the contract x of z equals p. So those will fail to interact. Similarly, for call syntax and for the persistent for. So before I go on, are there any questions? Cool. Let's see an example. So to kind of illustrate the difference between how contract and the for, persistent for, behave when they're deployed, assume this time that Alice is deploying a contract, right? X of z equals p, and that Bob is deploying a persistent for z coming on x to p. And they deploy these separately, so they're going to be paid for by Alice and Bob's wallets, respectively. Being put in par with S, the blockchain state, right? We see PHA and PHB, separate counters. And that X is fresh, so there's no activity over it yet, right? What we're going to assume for this purpose is that Bob's for executes first. So since there's nothing else there, Bob's persistent for is going to stick in the tuple space. And when it does, because we remember that fors maintain their balances, it's going to put PHB at a decremented value in with the continuation. Remembering that this allows the continuation to maintain its own balance for an arbitrary amount of time before it gets a message, right? So in this setting, I don't really have to worry about, or it essentially preserves asynchronicity, because I can put a continuation in the store and wait for an arbitrary amount of time until something else comes in and invokes it. And what we see at the bottom is that after the contract definition deploys, it essentially behaves like a persistent for. So where we see right here, double question mark z dot p, right? We essentially have the contract saying, after you give me p, or after you give me z, I'll run p. But it does not maintain its own counter, hence the downward tack, implying that it must be given some. So say concurrently, we have invocations running for both of these constructs. Say that we have x of c, which is calling the contract, given its initial flow value, ph of c, and then we have x bang d, which is executing the persistent for, or will ultimately trigger it. So when x bang d reaches z.p with ph of b prime, it's essentially going to require that the persistent read, similarly to the persistent send, is taken out and then put back, right? Because persistent read is equivalent to a number of single reads done in par. So essentially it accumulates cost every time that something triggers it, because we have to put it back into the store. Noticing that the persistent for maintained its own flow balance. And of course, that when we do the contract call x of c, we see that ph of c is threaded through to ph of c prime with the continuation. So it all works out, I think, very naturally. Of course, we should also mention that x of c, the contract call, or the reason that ph of c is decremented at all is because we have to execute the call. And that the reason, or essentially that you don't see the final value, ph of d prime, for the x bang d, but that is quantified as well. Any other questions? All right, cool. And there are, this is white screen. There are So there are a number of kind of open questions that we're still toiling over, but that we believe we have solutions for, but I haven't had a chance to formalize yet. Namely, the addition of a storage component to phlogiston, right? It's kind of an obvious point. Well, if I can just create a new name and then do half of essentially com event, if I can just do new x in x bang bang q, then I've essentially created a process that can never be interacted with. So what happens to that channel, and what happens to the message? Does it stay there forever? That's almost kind of begging for a DOS attack. So what we're currently in the process of is formalizing, essentially, in the same way that I gave the semantic rules for execution flow earlier, how storage flow will be integrated into the total cost of a program. So this is effectively rent, right? Question? Mike, I can't hear you, sorry.
Okay, you might have covered this already, so forgive me if it's a repeat. Is gas pricing always the same no matter how much processing you're doing?
The cost and flow, yes. Yeah.
So if I have one process that's doing a fixed height of, say, 100 rows of processing, and the next one's 100,000?
You said rows of processing?
Yeah, rows. So it's going through the contract process rows of data.
Oh, you're saying like if I deploy a program that like does more,
right?
Will it be the same cost?
Well, it could do it. It could do it different depending on how much time. First one goes through 100 rows. Mm-hmm. Maybe the next data set it gets is 100,000.
Sure. No, in fact, one of the kind of cool parts about being able to specify these things at the language is that it's kind of independent of, let me know if I'm answering your question, but that we pay essentially for all of the computational complexity that can be represented. So if your program does more, right, if it takes more steps with respect to the language definition, then it will be more expensive. Does that make sense?
It does. So the program will always stay the same. Mm-hmm. But in one instance, iteration, it may do a very little amount of work. It may do a lot of work. Yeah. And other times it may do a variable amount of work because you don't know how large the data set coming in is.
Exactly, right.
Okay.
Yeah. But if it does more work, then our cost model captures the additional complexity.
What if it's dynamic and you don't know how much data, like it's reading from a stream? Mm-hmm. How do you predict, because you want to set the right gas pricing or the amount of gas you're putting in?
Well, you set that initially. So you set that at the deployment. And once you set that, it's fixed effectively for all computations that use the counter that you essentially gave the initial program. Okay. So for the entire causal chain of events that gets set off by you executing your program, we thread through the same conversion rate, the same wallet, and maintain the flow balance for that. Yeah. Okay.
How is the flow purchased, or how do you pay for that, how does that happen? How is your balance subtracted for using flow, or that sort of thing?
Right, effectively, okay, no, excellent question. Let me back up a bit here. So here I simply kind of listed the way in which the conversion occurs, right? And for simplicity's purposes, left out the fact that in these deployments that you'll need to specify more information, right? Which is essentially code that allows you, that interacts with the purse and wallets to pay for the initial computation, right? And the conversion rate. So after all of the processing is done, after the initial rev is taken out of the account, 2 is what we're given, right? So it's the same as how it occurs essentially in Ethereum style gas conversion.
Well, so in the Ethereum style, gas price and gas limit are set on the transaction parameters explicitly, and then the VM removes that from your balance.
Yes.
So were you suggesting this is like one of the steps that you do before you do your actual computation? So it's sort of...
Yes, I'm saying that that's captured in deploy. That's captured in the deploy function. So when you call that, you call it with your wallet, and you call it with the conversion rate, and you call it with the phlim, all the same stuff. And then the same initial checks are performed to make sure that you have enough to cover the cost inside of your wallet, right? And the corresponding amount is taken out of your wallet, and then you're allocated the initial amount of flow.
So then does the wallet needs to have some logic for like going to the flow blessed contract or something like that and purchasing flow, or like how do you acquire?
No. There's no flow contract, right? We have to remember that flow is essentially just like a runtime value, right? So there's no wallet necessary for flow.
So you could view it as deploying, like, we recognize specific kinds of code, and you deploy a little bit of payment code that turns over some rev, and then that rev is gone not available for the duration of the computation. It either gets turned over to the validators, or we don't know whether or not you'll get a refund if you didn't use it all. But
does that mean the miner needs to do some introspection into the deployed code to determine what you're setting your gas price to do in order to?
No. So you'll have several fields in a deployment besides the code. So you'll have, like I mentioned, either some form of payment, either a key, and we only accept certain kinds of wallets, or a bit of code that, like, we recognize one of the following 3 forms or something like that, and you will specify how much you're willing to pay for flow. So you're not just deploying code. You're deploying other things with it.
In particular, deployment is an API that the node provides to off-chain clients. They invoke this thing, send a gRPC or whatever to the node containing the deploy command, the code they want to deploy, the wallet. It's got to be a wallet if it's coming from off-chain, right? It's got to be a public identifier to get at that wallet, the conversion rate, etc.
So one more thing, and this might stretch a little bit outside of the topic of this, but does that mean that you can't have sort of account security abstraction is the jargon we use in Ethereum development, but like could I deploy if I don't want SecP, I have my own crypto and I want to do account verification, authentication via that, am I able to deploy that in user space or yeah.
Yeah, so that's an excellent question. When you send a message to a contract, that is deploying code. So if you want to do a transaction, like send money from my wallet to that one, then you have to do some cryptography within the deployed contract that is wrapping the purse. So all of these crypto functions are going to be made available to be called from within contract code. It won't be up to the node or the blockchain to verify your command to the wallet as it is in Ethereum. It's rather client code that verifies that what it's receiving is valid.
So then in that case, whose balance gets reduced? Like if it's paying rev?
The balance of the wallet associated with the deployment.
So we haven't worked this out exactly, but one way you could see it working is you get to deploy a tiny bit of code that you see there's the code that you're going to run, and then there's a tiny bit of code that that we're going to use to extract payment. We set a much tighter bound on that. Right, you have like 10 steps to either come up with payment, or we're just throwing out the whole thing.
Okay, so I can go to my user space wallet, get like authenticated, and then that thing's going to say like I'm going to be paying for the flow. Okay, and then, so then how do you specify that you are going to be paying to the flow? Is that some system contract?
No. That's what I was saying. When you deploy the code, right? Like you want to run some code, you'll have to supply something that says here's how I'm going to pay for it. You deploy, right? Like so, if your rev is stored in a wallet guarded by a signature, right? You write the little bit of code that sends the signed message, gets back the correct amount, a purse with the correct amount, and hands it to the node.
And that would be written in Rolang, right? So that can be verified by the unforgeability of names and purses. So if like I can provide code, essentially, that transmits the purse across an unforgeable name. Tell me if I'm getting this right, Kyle. Across an unforgeable name, and because it's been written in Erlang, I know that that name can't be replicated, right? And since it can't be replicated, I know that it had to have come from the entity associated with wall.
So you can view it that like the Node software will write this snippet for you if you have a standard wallet. So you just say, okay, here you sign the transaction, you deploy the code, it comes from your balance. It all just kind of works. So don't worry too much about like exactly the details.
I want to worry about the details. That's
Okay,
what I'm here.
Well, then it's exactly like I explained. You deploy a little bit of code that accepts an address to send a purse, and you fill that purse with the amount of rev you're willing to spend. And if that doesn't go as planned, right, we make sure that runs before we ever look at what else you deploy. And we run that with a very short leash. You know, all blockchain systems have this problem where like they have you can DOS them. They have to verify payment before they can start debiting your resources. So like you just set a short leash, basically.
So if it doesn't like throw and it doesn't terminate, then that thing is an approval, and so now we know that you can continue doing the rest of your computation from there?
Yeah, so the node will basically run and make sure that, yeah, I now have more funds.
Cool. Good solution.
Within a smart contract, will you be able to control where the flow is coming from to get paid for? So we just talked about payer pays for the deployment that might cause execution of code. Within that execution, could this contract call other functions and have different purse used to pay for it?
Well, at least we hadn't planned, at least for the Mercury release, to include syntax that allowed users to specify inside of processes which wallets and were associated with a given process. And specifically because, I mean, assuming that we can kind of allocate everything naturally, right? If we make that assumption, then we have both options, right? We have the option to either pay for things together or to indicate payment or to not indicate payment, right? And those were essentially our two concerns, right? So by introducing and attaching semantics to the syntax we already have, at least we could cover both cases. So does that answer your question? If there's a more specific example, perhaps that could be more.
Yeah, so if you have contract A that you're calling and you're paying for, and inside that contract A, you're calling contract B, which offers to pay for execution, that can happen.
Yeah, you can call contracts inside of other contracts, if that was the question, yeah.
But the important difference was that you might have one that it's being paid for with some other purse than the purse that initiated the transaction.
That's right. You can set things up so that, for instance, the contract is waiting for payment with invocation, but then it can also have a for, which says, I am going to pay for this part. You can you can set up something like a replicated send that's loaded up with a whole bunch of phlogiston that's constantly sending to a name as soon as it becomes available, so a way of continually funding things. You can actually explicitly send a purse over, and then the contract invokes the deployment phase and provides the purse as part of that. There are lots of different ways of getting the payment semantics correct.
Right. So, for example, if we have, a contract that includes inside of it another contract definition and a for, right, then we should be able to see kind of how both things work. So, if assuming in par with all of this, right, so that I have X, right, which is invoking the contract, okay, then the flow and the wallet associated with the invocation are propagated to this contract, right? So they become essentially the default within the body of the contract, okay? For the for, we remember that if you've included an execution of the for, that you are indicating intent to pay, right? So the for will be paid for, essentially, by the user or by the flow in the wallet that was associated here. Contract does not indicate, the definition does not indicate that you're willing to pay. So this is not paid for by the entity that invoked this contract, right? What we're waiting for here is a separate invocation, A save C. And when that's called, then this will be threaded through, right? So think of it. So you can think of contracts in the same way as they work on Ethereum, which is like essentially the call return style, right? And when you call a contract, it just assumes that you want to pay for the contract, right? The only different thing here is the input term, which indicates that, yeah.
So I think I know the answer to my next question, but
Good.
but have you guys thought about at all allowing validators to accept payment in something other than Rev?
Ideally, yeah, we have thought about it. We would like for the protocol to be parametric in the token, but I'm not in a position to make any promises for Mercury.
Greg has said there will be multiple staking tokens. For Mercury, it will only be Rev, and there will always be a large preference for Rev. So you may be able to stake with Bitcoin, but you're not going to get as much phlogiston for it.
Thanks, guys.
Cool. All right. Yeah.
So I've heard this the last couple of days that Rolang should be like a general purpose programming language, right? Not just for the blockchain. Right. So what does all of the semantics still exist when I'm just programming something for my local system, or does contract and call not exist, or how does that work?
So yeah, for the blockchain in particular, yeah, this is specific to the blockchain, right? It's a blockchain specific problem. So yeah, so my answer would be that in absence of flow, contract and the persistent for become the same.
Except that in a persistent for you can do joins, whereas in a contract you can't.
Right. So yeah. So yeah. So that's actually kind of what makes that whole thing, or this whole thing, kind of work out nicely, is that in contracts you you can't do, what do we want that to be? Yeah, like joins, right? So you can't synchronize on multiple channels in the same input statement. Contracts only take a list of arguments, right? So yeah, so in absence of like kind of a flow framework, then contract is equivalent to persistent input with only one read, right? Cool.
So just to be clear, the payment stuff is a property of the runtime, and I mentioned in my talk that the blockchain runtime has special features about it that make it appropriate for the blockchain.
Right.
But you can imagine other runtimes, like the existing interpreter that we have out already, which has only the properties it needs to make sense of sort of the goal that you have.
Right, yeah. Cool, well, if that's it, thanks everyone.